In this module, we're looking at different properties in the coordinate plane and different theorems in the coordinate plane and using them to verify certain things in the coordinate plane. So first of all, let's remember that way back, I think in module 5, we learned that if two non-vertical lines are parallel, they will have the same slope. And what we're doing in this lesson is we're proving some of these properties that we were just kind of taking at face value before, but now we have a little bit more geometry under our belts and we're able to prove these properties. So here we're proving that if two lines are parallel, then they have the same slope. So we're starting with lines M and N being parallel lines that are neither vertical nor horizontal. And then we're picking 2 points A and B on line M and drawing a horizontal line through A. So notice how doing that kind of creates a triangle. And then we, at point D, the point where that horizontal line intersects line N, we have another triangle there. So we're extending it so that segment AC is equal to segment DF. And then I'm drawing a vertical line from C up to line M and then from F up to line E. So we're using these parallel lines because we know that when parallel lines are cut by a transversal, corresponding angles are going to be congruent. So angle BAC, that's this angle here, is a corresponding angle to EDF. So I know that they're congruent. And so based on those angles being congruent, and based on the way that this triangle was built, we built it so that AC would be equal to DF. We know that a horizontal line and a vertical line form right angles, so I know that those angles are congruent. So triangle BAC is congruent to triangle EDF by angle side angle. So then by CPCTC, I know that segment BC will be congruent to segment EF, which means that the length of BC is equal to the length of EF. Now we know from algebra that the slope of line M is going to be the length of BC over the length of AC, and that the slope of line N is going to be the length of EF, over DF. So the slopes of the lines are equal because of substitution property. We know that we could substitute BC for EF because of this statement. We know that AC and DF are equal because that's how we built them. So the slopes of the lines are equal, again, because of the substitution property. Similarly, we can prove the property going in the opposite direction, the fact that if they have the same slope, then that means that they will be parallel. Okay, so I have lines M and N having the same non-zero slope. So we set up a diagram very much the same as the diagram from the previous screen. So points A and B are just random points on the line, and we can draw a horizontal line through A and then a vertical line through B, again forming something that we're kind of calling a slope triangle. And if I'm extending AC so that it'll be giving me another slope triangle on line we basically set it up so that AC equals DF. And since line M and N have the same slope, then I know that BC over AC is going to equal EF over DF. But since I know that DF is equal to AC, I can use substitution to say that BC over AC is equal to EF over AC now. Now, if I multiply both sides by AC, that denominator, the denominator is going to cancel out, and I'll just have that BC is equal to EF. So let me take that and mark it in the diagram. And then once again, I can conclude that these triangles are congruent because I know that a vertical line forms a 90-degree angle with a horizontal line. So triangle BAC is congruent to triangle EDF by side angle side congruence theorem. And so by CPCTC, I know that angle BAC is going to be congruent to angle EDF. And once I know those two angles are equal, notice that they are corresponding angles with respect to lines M and N. And so I'm concluding that M is parallel to N, and it doesn't specify what the reason is. I think that reason is very important for you to know. Because I'm using the angles to show that the lines are parallel, we are using, okay, so N is parallel to N by the converse of corresponding angles theorem. So why can the slope criteria be applied to horizontal lines? Well, if we did the calculations for the slope of a horizontal line, the slope would be 0. So if I have two lines that have slope 0, then the lines would be parallel. Okay, so horizontal lines have slope of 0. So two lines having 0 slope have the same slope. So horizontal lines are parallel. Problem with vertical lines, notice it says explain why the slope criteria cannot be applied to vertical lines even though naturally all vertical lines will be parallel. We can't use the slope criteria because technically a vertical line has no slope. Vertical line has no slope, so slopes of vertical lines can't be compared. In example 1, part A, we are given this figure in the coordinate plane and asked to show that it is a trapezoid. So step 1 is to identify the coordinates of the points. You see that they did that. In step 2, they're using the slope formula to find the slope of AB and find the slope of DC. And when they did that, notice that those slopes are equal. So since the slopes are the same, AB is parallel to DC, and therefore it is a trapezoid because it's a quadrilateral width. And again, consider that a typo. it is a quadrilateral with exactly one pair of parallel sides. Similar kind of example in part B. This time I'm asked to show that it's a parallelogram. So again, step one is to identify the coordinates of the vertices. They've already identified two of them for us. R is located at 3, -2. And S is located at -1, 0. So they've already found the slope of PQ. Let's find the slope of the remaining segments. QR is going to be these 2 points that I'm plugging in. So that's -2 - 2 over 3 - 1, which simplifies to -4 over 2, which again simplifies. That gives me -2. Slope of RS, that's going to be, let me highlight what I'm looking at here. Finding the slope of RS, I'm going to be using those two coordinates. So that will be 0 minus -2 over -1 minus 3. That will become +2 over -4. This reduces to -1/2. Finally, slope of SP. I'm going to be using those 2 points. So that's 4 minus 0 over -3 minus -1. 4 minus 0 is 4. -3 minus -1 is -2, and that simplifies to -2. In step 3, it says to compare the slopes. So I noticed that the slope of PQ is the same as the slope of RS. So PQ is parallel to RS. And since the slope of QR is equal to the slope of SP, segment QR is parallel to segment SP. Therefore, quadrilateral PQRS is a parallelogram because it has 2 pairs of opposite parallel sides. It says, what if we knew that the lengths of PQ and QR were each the square root of 20? What type of parallelogram would that be? Well, let's look at where PQ and QR are in that figure. PQ and QR are consecutive sides of this parallelogram. So if I knew that the consecutive sides of this figure are congruent, then I could say that it is also a rhombus. In this your turn example, we're asked to do this problem on our own to show that JKLM is a trapezoid. By definition, a trapezoid has 1 pair of opposite parallel sides. Now, looking at it, I would hope that you'd notice JM and LK don't really look like they have the same slope, whereas ML and JK do. So those are the slopes that I'm going to find. Before I find slopes, however, I need to identify the coordinates of the points. Remember, that was step 1. So J is -2, 3. K is 4, 1. L is -1, 0. And M is -4, 1. The slope of LM is 0 minus 1 over -1 minus -4. And when I calculate that, I have -1 over 3. Let's find the slope of JK. That's 3 minus 1 over -2 minus 4. That's 2 over -6, but of course we're in high school, so we reduce our fractions, and when we reduce that fraction, we end up with -1/3. And since the slopes of these two opposite sides are parallel, the slopes are equal, that means that the sides are parallel. So JK is parallel to LM. So JKLM is a trapezoid. Here we're taking that to the next level and finding a missing coordinate. So in part A, I know that this is a parallelogram, and I'm given 3 coordinates, and I'm asked to find the 4th. So step 1 naturally is to plot the points. Step 2 is to find the slope of AB by counting the spaces from A to B. And so you see that they calculated the rise and they calculated the run. And so from point D, I'm going to count the same units. So let me clarify something a little bit here. Slope of AB equals 5 over -3. So I'm going to count the same kind of rise and run from D. So from D, I'm going to rise 5 and run -3. And that point, 2, 4, I label it as point C. And then it says in step 4, use the slope formula to verify that BC is parallel to AD. So they did that here. They found the slope of BC to be 1 over 4. They found the slope of AD to be the same thing. Therefore, they conclude that yes, that 2, 4 that they found is the 4th point. And if we connect the dots here, we see that it looks right. It looks like it's a parallelogram. Same kind of problem in part B with a few more blanks for us to fill in. So again, I know that it's a parallelogram, and again, I'm given only 3 of the points. So P at -3, 0. Q at -2, 4. R at 2, 2. and I need to figure out where S is. So I'm going to count the slope of PQ so that I'm counting from Q to P, because eventually I'm going to be counting from R to S. So from Q to P, that is a rise from 4 to 0. That's a rise of -4 because I'm going down from Q to P. And then the run from Q to P is -1. So I'm going to rise and run in the same manner from R in order to figure out where S is. So from R, I'm going to rise -4, so 1, 2, 3, 4. And I'm going to run -1. And so here is where I'm conjecturing that point S will be at 1, -2. Let me fill in a few of these blanks. A rise of -4 from 2 is -2, and a run of -1 from 2 is 1. And so we found the point 1, -2 in that manner. And now in step 4, we're going to confirm that QR is in fact parallel to PS. So QR, that's these 2 points, that slope will be 2 minus 4 over 2 minus -2. So that's, they already have a negative sign for me. That's -2 over +4, which reduces to -1/2. The slope of PS is this point and this point plugged into the slope formula, so that's 0 minus -2. And -3 minus 1. And that will be 2 over -4, which reduces to also -1/2. So the coordinates of vertex S are 1, -2. And again, when we connect the dots,